Hello AP Calculus AB students, Mr. Record here. Going to take a look at our first video from topic 6.2, which is entitled Approximating Areas with Riemann Sums. So you have this new phrase, Riemann Sums is the way it's pronounced, that we're going to talk a little bit about the history and where the name Riemann comes from here in the video. But you're basically going to get an introduction to more ways, let's say, to find the area under a curve, which we just started to talk about the importance of in topic 6.1. So let's take a look at what this idea of the Riemann sum is all about. Now, if we remember where we left off with topic 6.1, we had this particle Q, and we said that it moved along a straight path. And if you recall, in our example 2 from lesson 6.1, we were given the graph of the velocity of a moving particle. In that case, it was moving particle P. And that moving particle had a constant velocity. In other words, it had a straight horizontal line depicting its velocity. And that was a very easy graph to work with because we had deduced the fact that if we wanted to find the total distance traveled, all that we have to do is find the area under that curve. Essentially, what we're doing is we're multiplying the dimensions of the vertical axis and the horizontal axis together. And when you do that in a situation where you have, let's say, feet per second, for lack of a better combination, and you have seconds along the t-axis, whenever those two units are multiplied, the seconds cancel and you get feet, which would be a depiction of the total distance that we may have traveled. Now, the problem that we're faced with often is that the graph of our velocity is not that nice line that we can use wonderful geometry formulas for. In this particular instance, this particular curve, v sub q of t, is actually denoted by this equation, 0.5 t squared plus 1, which means we have a quadratic, which is a parabola. And so we're being asked to now think about what would be the area under this curve from 0 to, well, what's the total distance traveled from 0 to 2? That would take us all the way to here. And this yellow region's area is what we're looking for, which doesn't lend itself very well to a nice geometric formula. So some other things are going to have to happen. And so let's talk about those things. It says, although there are many possible techniques to approximate the area under a curve, we are going to use rectangles or trapezoids throughout AP Calculus. In this particular video, we're going to focus on rectangles only. We'll move into the trapezoids a little bit later on into some future videos. So what is it all about? What does it mean to approximate the area under a curve using rectangles? Well, when you use rectangles to approximate the area under a curve, you got to decide on a few things in advance. Number one, how many rectangles will we use? We're going to call these subintervals. Early on, that number is going to be provided to you. Later on, it's not going to be so obvious what that number is, and so we're going to have to do some other things. And then number two, how are we going to determine the height of each rectangle? And you actually will have three options predominantly in the realm of this particular course: left endpoints, midpoints, and right endpoints. We'll talk a little bit about midpoints later on. And that drives this whole notion of approximating the area under a curve. Notice I said the word approximating the area under a curve using rectangles. So let's take a look at our example one, which is going to use that velocity equation, v sub q of t, that we just talked about, and finding a various areas in this case. So let's read this. It says, use a left Riemann sum with one subinterval to approximate the area between the curve v sub q of t equal 0.5 t squared plus 1 and the x-axis from t equals 0 to t equal 2. Essentially, we're thinking about finding the distance traveled here. right? Even though we didn't innately state that. Right? Let's focus a little bit more now on the process rather than what the end product really means here. So one subinterval. So I'm going to underline some important things. We have one subinterval, which means one rectangle, and we are going to use a left Riemann sum. So those are the two important components to this question. We know that our interval starts at 0 and ends at 2. What we'd like to do is to try to draw a rectangle. Well, how do you draw a rectangle underneath this very strange, or in and around this very strange curve? And that's a great question. Well, one thing that I would tell students to do is to go ahead and take those two endpoints and draw vertical segments that go all the way up to the curve. Because we're only going to use one subinterval, I have a really fancy way to figure out what the width of that subinterval is going to be, although it's not a big mystery here. But if you basically take the beginning point, which is referred to often as A, and the end point often referred to as B, and by those points I'm talking about along the t-axis, we could subtract those from each other and divide by the number of subintervals, which I'm going to call n. Now in this case, B is 2, A is 0, as you can see from my depiction here below, and my n is 1. That certainly means that your width of your rectangle is going to be 2, and that's not a mystery because you can see that width is 2. The problem is the height. How do you determine the height? Well, that's where you have to look at the type of Riemann sum you're going to be taking. In this case, a left Riemann sum means that it's the left side of this rectangle, which is going to occur at this point here when we reach the curve, that's going to then serve as the top portion. And so there we have our rectangle. And that will be shaded in, color it in this green, and we're going to find the area of that particular rectangle and use it as the approximation of the area underneath the entire curve. Now, I didn't say it was going to be a good approximation, but that's how you would answer this question. And so we would say, if we write this up, our area, sometimes I like to use a subscript that denotes what kind of Riemann sum I'm using, L in this case. So this area using a left Riemann sum would be approximately equal to, well, all I would have to do at this point is figure out what is the width of this particular rectangle, which we already said was b minus a divided by 1, which is 2. And then I just have to calculate the height. And the height is just determined by using the x value of 0, which denotes the left endpoint, and inserting that in for this value of t. And I should have said the t value instead of the x value. It is the horizontal axis value. And so that 0 gets plugged in. And I know it's not going to be a big mystery here to see that that's just 0.5 times 0, which is 0 plus 1, which is 1. And so you're going to get 2 times 1, which of course is 2. And as you can tell, this green shaded region certainly consists of 2 blocks. And thus the area is 2. And you probably could have just looked at that to determine the answer is 2 without having to go through this numeric process. But as we have more and more rectangles, this numeric process is probably going to be important. So as I said before, hey guys, it's not a great approximation. That's not what I'm really interested here. I'm just interested in answering the question that was asked. You only get one rectangle, define the height by using the left endpoint, and then figure out its area. Now, let's stick with this left endpoint idea and look at our example 2. But the only difference now is that we are going to adjust the number of subintervals, and we are now going to go up to 2. So we're talking 2 equal subintervals, and again using the left Riemann sum. And let's denote that our function v sub q is the same, and our boundaries are still from 0 to 2, which means that the width b minus a over n is still the same, right? 2 minus 0 over 1 is equal to 2. Now, from a picture standpoint, what would that look like? Well, actually, I take that back. I'm sorry. Let's go back to this, you guys. My n, my subintervals is 2. So I'm going to change this, if you don't mind. 2 minus 0 divided by 2 is 1. Otherwise, we would have been doing essentially the same problem. So hopefully you see now that there are going to be 2 rectangles. Each will have a width of 1. So I still start at 0 and I still end at 2, but now this 1 is going to be important. So I want to draw vertical segments that go up to the curve, like such. And I don't see rectangles, right? You don't see rectangles, but we're going to make that happen here by capping these 2 strange shapes off with a horizontal line segment to make rectangles. Well, how do you cap them off? We use a left Riemann sum, which means we take the left side of each shape, and I'm going to call this shape number 1 and this shape number 2. And from the left side, we move over to the right, and boom, we've capped it off. Not so much with a rectangle here, that's more of a square, but it's the same idea. Square is a rectangle. And we do the same thing over here, which puts a point right there on the curve. We move to the right, and boom, there we go. And if I were to shade in both of these shapes, the area that's depicted by this shaded region would answer our question. Again, it's not an exact value because, of course, we're missing out on a lot of space here. Maybe we're doing a little bit better job than we did earlier, but that's not the point. The point is using this approximation technique to find the area that's given. So let's see what our setup looks like. Once again, our area using a left Riemann sum is approximately. I'm going to take the width of each rectangle, which is 1, and then I'll just multiply it by the sum of the heights of both rectangles. That way I don't have to take width times length plus width times length, especially if I know my width is going to be 1 each time. It's going to save us a little bit of writing. So what are the 2 values of t that are important in this problem? Well, using the left endpoint, I have a 0 and a 1 that are going to come into play. Well, we've already done the 0 a moment ago, but I'm going to go ahead and write it up again. We replace the t with 0, like such. And I think I might take that parenthesis off. And then we add, and then I'm going to do the same thing, except now I'm going to replace the t with a 1, like that. And there I have the sum of those 2 heights that are each going to be multiplied by 1, the width. Not going to change much there, is it? And that's going to give me my area. So as you can see, the first part of this is still going to give us a 0 plus 1 in this case. First rectangle is an area of 1. And then this one's going to be a little bit trickier because I got 0.5 times 1 squared, which is 0.5, plus 1, which is 1.5. I'm going to go ahead and leave this in decimal notation because it's not going to be too difficult to compute. And once I do all that work, we get an answer of 2.5, or 5/2. And that ends up being the area of both regions 1 and 2 added together. It's the area of that blue region. A little bit bigger than the area of the green region, which means it's probably a better approximation towards what the final area is under that curve. All right, let's keep going with this idea. We have another version of this, which is now going to ask us to use a right Riemann sum with 2 equal subintervals to approximate the area. Again, the same curve above the x-axis from time 0 to time 2. So because we're using 2 subintervals, the idea of the width is still b minus a over n. I'm not going to lose that fact. And I'll actually compute it correctly this time. It's 2 minus 0 over 2, which means each rectangle has a width of 1. Well, that shouldn't be a big mystery because that's what we saw before. So obviously 0 and 2 are going to be very key components to this problem because those are our endpoints. And because each interval is going to have a width of 1, this 1's going to come into play. As always, we draw our little segments up to the curve as such. But now things are going to change because this problem is wanting a right side Riemann approximation, which means now to cap off these shapes, I'll call them again shape 1 and shape 2, we don't go from the left side over to the right, but we'll start at the right side and move over to the left as such. And I'll do it again up here, right side over to the left. Now what that means is that we're going to have to sort of tack on this extra little dashed line there to get this rectangle fully assembled. And now I can go ahead and shade in all this region. And this is what we're trying to find now, guys. We're going to find the area of these two shapes, and we'll just end up adding them together. Now you're probably noticing, wait a minute, man, that's going to be too much area. That's like more than what we really would like, more than what's underneath that curve. And yep, I understand that. It happens. Right, we'll address the idea of above and below the actual area a little bit later on, but we just want to answer the question that's being asked. And so let's set up this particular area formula. Might use the subscript r, and we know that the width is going to be 1 of each of these figures. And because my key players now are 1 and 2, right? I'm going to use 1 and 2, since it's a right Riemann approximation, to plug into this particular formula. I have 0.5 times 1 squared plus 1, and then I'll add to that 0.5 times 2 squared plus 1. Okay, so let's see what we've got. We have 1 out in front times, well, 0.5 times 1 squared plus 1. We already talked about that. That's 1.5. And then over here, well, let's see how this is going to work out. 2 squared is 4. 0.5 times 4 is 2. And then 2 plus that 1 is 3. Hopefully you guys follow that okay. And then, of course, 1.5 plus 3 is 4.5. And then multiply that by 1. You still have 4.5, or 9/2 if you wanted to express this as a fraction. And that would indeed be the area of these two magenta colored regions, which is the approximation of the area under the curve. Certainly it's an over approximation, but that's okay for right now. Now, I have a little think about it here I wanted to discuss with you. It says, what do you think would happen with our approximated area, that would be the area of these rectangles, if we were to use more and more rectangles? You've only seen 2 rectangles at this point, but if we used more and more of these, what do you think would happen? And maybe you're stumbling upon the idea that the area approximation very likely would be closer to the actual area under the curve. All we need is to make these rectangles a lot thinner and throw a lot more of them in there, and therefore a lot of this extraneous area that we were getting, or the lack of the area that we were getting, say when we were using the left endpoints, would not be quite as prominent. And you're going to see that's indeed going to happen. And this is where this is ultimately going to lead. A little bit of history about this idea of the Riemann sum. It's an idea that was presented by George Friedrich Bernhard Riemann. He was a German mathematician. He did most of his work in the area of non-Euclidean geometry and differential equations and number theory. But it was basically his results in physics and math that formed the structure for which what Einstein's theory of relativity is based. So he's certainly a big player in the world of mathematics and science. And he was one of the first people to really look at these shapes, attach his name to it, and run with it a little bit, so to speak. And you'll notice that his contributions to the mathematics world was in the early to mid 19th century, which was a long after, almost 200 years after calculus had originally been discovered. So anyway, I hope this helps a little bit. I hope it gets you a little bit of an introduction to Riemann sums. You're going to be working with left endpoint Riemann sums, right endpoint. You might be using as many as 2, 3, 4 different rectangles, but you want to structure them just the way that you've seen in these particular examples. We've got some more videos coming up over this idea. We want you to tune into those. And as always, thanks for joining.